So what did we decide then? Do quantum computers really serve a purpose? We saw in the last video that a sufficiently powerful quantum computer could jeopardize our digital signature, online banking, and many more things. But we said that we are still very far from that scenario because the quantum computers we have today are too small to pose a threat to these systems. And now we ask ourselves, do these quantum computers we have today serve any other purpose? The first thing we need to know is why a larger quantum computer is useful for more things, which we have taken for granted until now. But we are here to explain absolutely everything, even if it seems obvious. And in quantum, there is always an unexpected bonus. So here we go. When you buy a computer or a mobile phone, if you are one of those people who look at the specifications in detail, you will see that there is something called RAM memory, which is measured in gigabytes. Broadly speaking, RAM is the working memory of the computer, meaning how many little numbers it can operate on at once. The one in my brain, I can tell you, is scarce, as I'm terrible at mental calculation because I can't retain numbers in my head. I even have trouble multiplying two-digit numbers. But if I could retain more numbers, I could do more complex calculations, right? Maybe I could multiply three-digit numbers with carrying things like that. The same thing happens in my computer. The larger the RAM, the more things the computer can do. That's why in computers from 10 or 15 years ago, you might not have been able to make a Zoom call with 20 people because that requires a lot of simultaneous calculations and they couldn't keep up. While one that comes out of the store today will have no problem displaying the cameras of all those people. Well, with quantum computers, it's the same, but with qubits. The more qubits they have, the more powerful they are. However, there is a fundamental difference between having more bits and having more qubits. By adding a bit, you increase the computer's power a little. And if you want the computing power to be double, you have to double the number of bits. Well, with qubits, if you want to double the power, you just need to add one qubit. So as you keep adding qubits one by one, the power of your quantum computer doubles at each step. That means it grows very quickly. In fact, it grows exponentially. Do you remember when the COVID infection curve was growing exponentially? That was when each infected person passed the virus to two others, for example, right? Well, it's the same here. When you add a qubit, the computer's memory doubles. Why? Because if you remember from the first video, a qubit is a mix of 0 and 1, where I can choose what proportion goes to 0 and what proportion goes to 1. But if I have two qubits, then I can combine them however I want. That is, I have a mix of 4 terms, 0, 0, 0, 1, 1, 0, and 1, 1. And that gives me twice the possibilities of having just 0 and 1. If I have 3 qubits, then I have 8 terms, 0, 0, 0, 0, 0, 1, and so on up to 1, 1, 1, which you can count at home. The important thing is that every time I add a qubit, I go from 2 terms to 4, then to 8, 16, and so on. It sounds wonderful, but like everything that sounds too good to be true, there's a catch. And that is, as I also mentioned a few videos ago, qubits are a bit unruly, and it's challenging to ensure they maintain their quantum behavior. A lot of code is needed. Creating a vacuum, in short, isolating them from the environment as much as possible. The more qubits we add, the more complicated it is for them to maintain their quantum behavior. The more qubits, the more sources of error. In short, it's not that pretty. So what do we do then? Well, it turns out there are ways to take several qubits with the errors and organize them to create a sort of virtual qubit without errors. Well, almost without errors. In short, if there is the algorithm you want to implement needs a few qubits in the abstract, to do it in real life, your computer will need several more. If we take this into account, the computing power of the computer doesn't actually grow exponentially with the number of qubits. But okay, the point is that it does grow, and it remains true that for every qubit you add to your quantum computer, the computing power increases much more than for every bit you add to a normal computer. Now there is a certain race in quantum computer research to build the largest one. But of course, the size is not the only thing that matters. What is really interesting is what you can do with it. To measure this, the concept of quantum advantage has been coined. If you build a quantum computer and have it solve a specific mathematical problem and demonstrate that a classical computer would have solved it exponentially slower, then you have achieved quantum advantage. For example, Google in 2019 made headlines everywhere because it was the first company, as they claimed, to achieve quantum advantage. What had they done? Well, they chose a mathematical problem and argued that a classical computer would take a very long time to solve it. Specifically, economically, they said it would take on 10,000 years. Then they took the quantum computer they had just built, set it to solve the problem, and in 200 seconds, which is a little over 3 minutes, it had the answer. The difference is remarkable, isn't it? 200 seconds versus 10,000 years is not bad at all. And it turns out that was an exponential difference for that problem. That's why they said they had achieved quantum advantage. Well, the criticisms didn't take long to arrive, not about the quantum computer, but about the classical part. IBM, the major competitor in this area, responded the same day saying that one of their classical computers would take 2.5 days to solve the problem. Okay, it's 2.5 days are not 200 seconds, but the difference is much less dramatic. And shortly after, more research articles came out providing classical ways to solve the problem in very reasonable times as well. Well, the next entity to enter the playing field was the University of Science and Technology of China in 2020. They didn't want to fall into the same trap as Google and looked for a mathematical problem for which they practically had a demonstration that it couldn't be solved faster on a classical computer. I say practically because a mathematical demonstration is something completely irrefutable.
Here, what they had were very solid arguments that did not amount to a proof.
But anyway, the recursive DNA, they managed to convince the scientific community that the problem was difficult to solve for a classical computer, and the quantum computer they built managed to solve it 10,000 times faster. Again, headlines everywhere, quantum advantage achieved, everyone very happy. And of course, the criticisms were not long in coming, although this time they were more expected. It turns out that the quantum computer from the University of Science and Technology of China was specifically designed to solve that particular mathematical problem and was not useful for anything else. The processor was not programmable because it did not work with quantum gates like the ones we saw in the previous video, but in a different way. It would have been better to achieve quantum advantage with a computer that could be used for anything. But hey, what they did has its merit. Since then, there have been other announcements of quantum advantage, each with its own caveat, and the race continues. In any case, the mathematical problems chosen for these things are usually quite obscure. I mean, outside the academic field, they are not very useful. And it is very, very difficult to find a mathematical problem that is exponentially more difficult for a classical computer than for a quantum one, and on top of that, to build a quantum computer that solves it, and also for the problem to have some utility. You have to get many qubits to work together, which is physically complicated, and also perform quite complex mathematical calculations to convince yourself that the classical is dramatically slower than the quantum. But I don't want you to live with the disappointment that quantum advantage is so difficult to achieve that quantum computers are practically useless. There are many other advantages we can achieve with these computers that are more attainable, and we will see that in the next video.